No. Yeah. Hello. Hello all. I hope you all will be watching this video. So today is the fourth week, and in this week I'll solve the assignment three. Now, the first question is I'll have look into my PDF, the assignment 3 PDF. You can go back simultaneously, or you can, if you are watching the video, then you will be seeing the questions as well. So, the first question is, consider the homogeneous superconductor. The order parameter is independent of the position variable R in absence of an external magnetic field B0. The free energy near the transition temperature Tc is written as this. Fs or Fn is the free energy of the superconducting normal state. Alpha and beta are coefficients. What is the order parameter? Psi 0 to that minimizes Fs. Minimizes means derivative or differentiation we have to do. Or and what is the Fn minus Fs at this value of psi 0? Okay. So So the free energy in the superconducting state is given by this. This is question number one. If Fs equals to Fn plus alpha psi square plus beta psi to the power 4. I can do this, I guess. Hmm. Okay. Now, Fs and Fn are the free energies. These are the free energies of the superconducting and the normal states. Right? This is for superconducting state. This is for normal state. Free energy. Now alpha and beta are the sorry, alpha beta are the material dependent coefficients. And psi is the order parameter. that describes the superconducting state. Right. Now, to find the equilibrium, we have to do derivation. So basically, what we have to do a minimization of Fs with respect to psi means dFs by d psi, and minimization means it should be 0. Right. Now, d by d psi Fn plus alpha. Now, each term we have to do Mm. So solving for a psi, it would be if alpha and beta are the coefficient, we'll take it out. Then 2 alpha psi plus 4 beta equals to 0. Then if we take alpha also out, then 2 alpha plus 4 beta alpha, sorry, if we take the psi out, then psi, the non-trivial solution will be what? So 0 minus alpha by 2 beta, right? Since superconductivity only occurs at when psi naught is not equals to 0, that is only valid if alpha is lesser than 0, right? Means minus minus, it will be positive. Now, substituting this psi 0 value in the Fs equation, the equation was this. If we take it as psi 0, Fn plus alpha psi 0 square, right? This was the same thing. Minus alpha by 2 beta. This value only we are putting. Plus beta is this is the whole square of this. Then Fn minus alpha square by 2 beta minus plus alpha beta into 4 beta square. Means 1 beta will be gone. Means it would be Fn minus alpha square 4 beta. This is alpha square, no? Plus, sorry, 2 beta plus 4 beta. Means Fn minus alpha square by 4 beta. Hence, Fn minus Fs would be alpha square by 4 beta. So, this is the condensation energy. Right, so this is answer of A and this is answer of B. 1A and 1B. Now, the second question is, sorry, 1 second. The second question is, in presence of an external magnetic field, in presence of an external magnetic field, B external, write down the first and second Ginzburg-Landau equations in terms of the order parameter and the vector potential that characterizes the magnetic field. Okay. Now, this GL equations is basically, what does this tell? This tells the behavior of a superconductor at a critical temperature. Tells us the behavior of a superconductor near the critical temperature. Now, the first GL equation is alpha psi plus beta psi square psi plus 1 by 2m minus I h naught that minus qa square psi equals to 0. So this equation describes the variation of the order parameter psi in presence of the vector potential A. Now the second GL equation is, this is a cross product BQ by MC psi star minus IH is QSI. So this is basically tells about the superconducting current density. So only this two they have asked. Yeah, fine. So then third question is, assuming the coefficient alpha to have a temperature dependence close to Tc given by alpha t, it's equals to this. Alpha naught is constant. Using GL equations, find an expression for the coherence length. Okay. So to derive an expression for the coherence length, we have to put a value as 0 in the first GL equation. This is the GL equation I have already written. Plus A alpha plus B equals to 0, where alpha is minus alpha naught in superconducting state. Now the coherence length square, this value is this. Right, now you have to take, you can assume that this is f, this term, this whole term means mm, b by alpha, or alpha psi square, taking this as f square. Then the equation would be double derivative minus f plus f cube equals to 0. Now if we multiply with f prime, it would be we are multiplying with f prime. Okay. Now it would be x plus to, equals to 0. Then This would be C. C is any constant you can take. Now, this is it is written already. mm, Far from the boundary, right? So it should be zero. If prime means psi prime should be zero. Then this also means f prime, right? So this means f square is 1 or psi square would be from here. Psi square would be just the reverse one of this one. Now, if we take this equation as 1, this is 1, and this as 2. Now, equation 2 will be so they have asked using geometric equations, find an expression for the coherence length. Right. Now, solution would be so the solution of this is also done, I guess. Solution would be f equals to tan h x by root 2. Hence, psi would be and in question it's given alpha t equals to alpha t minus tc. Right. Then the coherent length equation would be yeah. The next question is present schematic plots of order parameter, flux density, diamagnetic energy, and consideration energy at the normal metal superconductor junction as a function of the distance. Now, order parameter is psi, right? We have no. So psi changes from zero in the normal region to a finite value in the superconducting region. And flux density, it shows the flux density means penetration of the magnetic field will be there. And diamagnetic energy means related to uh, expulsion of magnetic means superconductor is always a perfect diamagnetic. So it shows the expulsion of the magnetic field, total expulsion. And condensation energy is the energy difference between the normal and the superconducting state. So we have to draw structure. So it's already there in the literature, so I'm just copying it from the literature. So let's say this is the superconducting state, this is the normal state, right? So this is how flux density works, and this is how order parameter works. And for if this is the normal one, This is the superconducting one. When the diamagnetic energy increases, but the energy gap is hc square by 8 pi. Whether the opposite is the condensation energy, and this energy gap is also 8 pi. Right. So they have asked present symmetric plots of order parameter flux density. So diametric energy as the atom as a function of distance. Okay, we have to draw this much only. Then the next one is explain the experiment. Okay, with schematic plots of absorption of electromagnetic radiation for determination of the superconducting gap. What is the magnitude of the gap in millielectron volt and in Kelvin in conventional superconductors? So, mm, when an electromagnetic wave is incident on a superconductor, absorption wave frequency you know, I guess. So, it's this to del. Del is the superconducting gap, right? And for conventional superconductors, del is 1.76 kb into Tc. So here, this is unit is Kelvin. So here by this also we can detect in Kelvin unit. Okay. So basically, what happens is radiation of frequency is in almost like 10 to 11 order of Hertz is guided into the small cavity made made with superconducting material. Now within this cavity the radiation is reflected many times before it comes out and get detected by a detector at a fixed temperature. Let's say when T is lesser than Tc, like below critical temperature, the Is and In, the intensity of the radiation detected corresponding to the superconducting and normal state. So intensity of superconducting state we can write that as Is, and intensity of normal state we can write it as In. Now Is, if we want to show Is minus In by In, whereby In means the difference with respect to the normal state. So the diagram would be, see if this is the frequency. See, this value is almost fixed 10 to the power 11, and this is also 10 into 10 to the power 11. Frequencies unit is Hertz. So the gap in milli electron volt, it would be around 10 millivolt. And the in Tc term, it is 15 Kelvin. These are all the like from book only I took these things. So you can refer to those books. And the sixth question is explain ultrasonic attenuation experiment. that demonstrates the phase transition from superconducting to normal state as a function of temperature. Why does sound passes through unattenuated in a superconductor? So ultrasonic waves interact with electrons. Those are conducting electrons in the metals, leading to attenuation due to electron phonon scattering. Right. So ultrasonic waves interact with the conduction electrons. Conduction electrons in metals, leading to electron phonon scattering. Now, in the superconducting state, a gap opens, right, in the electrons excitation spectrum, altering the electron phonon the interaction. Now, why does sound pass through the unattenuated like in a superconductor? So in the superconducting state, the Cooper pairs form. Cooper pairs, those are basically electron pairing only. So Cooper pairs, the formation of Cooper pairs leads to separation of the quasi-particle excitations that typically interact with phonons. So this means that below critical temperature, uh, the sound wave can travel with minimal loss, making superconductors excellent low loss acoustic mediums. So, whatever this experiment, ultrasonic attenuation experiment, this experiment like gives us the evidence, gives us the proof of the superconducting gap and the transition to a phase coherent superconducting state, right? So, uh, from this experiment, what do we see? So, we see that above, I'll just write the key findings or the observations as we write in reports. Above, we see, above, we see ultrasonic attenuation follows a normal metallic behavior due to electron phonon interactions. Now, below TC, attenuation drops due to the formation of superconducting Cooper pairs. What happens then? Scattering lessens, scattering reduces. Now, the third observation would be like the reduction in attenuation is linked to the superconducting gap. How should I write this? Reduction of in attenuation is linked to the superconducting gap. As phonons with a high energy, like below 2 delta, cannot break the Cooper pairs, right? There is a certain threshold, like power needed. So, leading to this, an almost transparent medium of ultrasonic waves, like we create. Phonons with energy below 2 delta can't break Cooper pairs leading to uh, transparent medium of ultrasonic waves. Right. Now the fourth finding would be stagnation coefficient follows an exponential decay. Okay. Like below TC. So this is we write as this. And why does the sound passes through unattenuated in a superconductor? That's what I told that in a superconducting state means Cooper pair formation is must. Right, Cooper pair formation is must. So for Cooper pair formation, due to that, leads to quasi-particle excitation, which means it interacts with phonons. Right, this means that below TC, this means that below TC, sound waves can travel with zero loss or minimal loss. This results in application. What is the application? Application means superconductors will be an excellent low loss acoustic medium. Okay, so this experiment they gives us the proof of the superconducting gap with the like transition to a phase coherent superconducting state. Now, seventh question is what are the utilities of tunneling experiments in normal superconductor junction systems? Describe the phenomena of reflection. Yeah, reflection in a NS junction, normal superconductor junction. How does it contribute to the zero biased conductance? Okay, so tunneling experiment of the normal superconductor junctions. This gives like this tells us the about the superconducting properties and like the DOS, energy gap, in energy gap, etc. So tunneling experiment in normal superconductor junctions. This gives us about superconducting properties like DOS means density of states, energy gap del, etc. Now the first question is what are the utilities? Utilities, so the measurement of the superconducting gap, del measurement. So by analyzing the tunneling conductance, we can do that. Now DOS measurement. So DOS can be measured by tunneling microscopy. So tunneling microscopy will tell you that the electron density of states where this present in the superconductors. Now the third one is coherence effect. Now the shape of the conductance spectra helps in understanding the electron pairing mechanism. So you'll do that and you'll do these measurements and you'll get the data. Now from the data you can look into the like the conductance spectra. If this is like the shape that will tell you about the electron pairing mechanism. Tell you about electron pairing mechanism. Describe the phenomena of reflection in NS junction. Okay. So Andrew reflection occurs at the interface of the no, like NS junction means where an incident electron from the normal state is retroreflected as a whole, forming a Cooper pair in the superconductor. So this is question number A. This is question number B. And this is about Andrew reflection. So this happens at is retroreflected as a whole, forming Cooper pairs. So if the energy I told, if the energy is lesser than the gap, it cannot be tunneled directly. No direct tunneling. So instead, if it is combines with the another electron to form a Cooper pair in the superconductor. Okay. Now, uh, the next is the missing electron, which is get replaced by a hole with opposite momentum. Okay, so basically what happens is this this doesn't happen. The if an energy is of an electron is lesser than the gap, that is not like what's say considerable, right? So what does it do? The missing electron, so it combines with another electron to form a Cooper pair. The superconductors. Now, this missing electron, we just got replaced by a hole, which so this is it. This will be the observation for the Andrew reflection. Third question is there. How does it contribute to the zero biased conductance? So zero biased conductance means uh, this leads to an enhanced subconductance, right? Now, enhanced conductance we can use to prove as an unconventional superconductors. So yeah, this is the seventh one. Then the eighth question would be explain S versus D wave order parameter symmetry. Write down a VCS gap equation for the D wave. And you don't need to summarize it. Fine. So S wave and D wave superconductor. So S wave is conventional BCS superconductors, which has isotropic gap in momentum space. So this is the conventional BCS superconductors, and this is the unconventional one, or you can tell it high temperature or high temperature superconductors. But like mostly like cuprates and all. So in S wave, we have isotropic gap. And for this, we have anisotropic gap of phase. with nodes, where y nodes, when at nodes, the gap vanishes, right? And now they have asked for the equation. So BCS gap equation for the D wave superconductors. Yeah. For the D wave symmetry, it will be right here. Okay, is the summation of VK K prime del K prime to I'll just explain and let me write it first. Then H E K prime to KBT. Okay, so del K is the gap function. Del K is a gap function. VK is the interaction potential. Potential. Now EK is the quasi-particle energy. And KBT, of course, the thermal energy term, right? So this equation tells us about the pairing mechanism of the unconventional cuprates. Those are unconventional superconductors. Also, unconventional is iron-based superconductors. Those are unconventional ones. So, and the D we call it D wave ones. Okay. The next question is write down a T JU model in second quantized notations and explain various terms. Write down the Hamiltonians in the K space and extract interaction term that can facilitate a pairing between electrons needed for superconductivity. Do you see a D-wave pairing term? Okay. So TJU model, no? TJU model in second quantized motion. Motion, not motion, rotation. Now, this model actually describes the correlated electron systems relevant to high temperature superconductors. Okay, so the equation is and now I'll explain. I is T is hopping integral describing the electron movement. Now J is the spin exchange interaction. This helps in electron pairing. And U is on-site Coulomb repulsion. So this one only the first portion, 9A. On 9B, they are asking write down the Hamiltonian in the K space and extract interaction term that can facilitate a pairing between electrons needed for superconductivity. So if we rewrite the Hamiltonian in momentum space, that equation, so it will be like this. I guess in earlier class we have done this. So for certain conditions, this interaction also favors D-wave pairing, like at high temperatures, superconductors. This also acts as the Hamiltonian when D-wave pairing happens. Now, the last question is list out a few stoichiometric compounds that yield transition temperature larger than 50 K from both cuprate and iron based superconductors. So I have few lists. So for cuprates, we have YPA2CU3O7. YBCO we also call it. The TC is 92 Kelvin. Now another one is PI2SR2 CaCu2O8 and the TC is 108. Now for iron based superconductors, of course BaFe2S2. This one doped with potassium, this has the highest one. And FeSe with pressure, like when applied pressure, this shows the TC of around 50 K. So basically cuprate Fe both are like this layered materials. This no. So this allows the so the since they're layered, so electron correlations happens more, and that strength of electron correlation like leads to unconventional pairing mechanism of the electrons. Like that's why we called it not the BCS superconductors, but the which does not obey the BCS rule. So unconventional superconductors, and these are also often found at high temperatures. So this was about today's class. So we solved the assignment 3. I think the assignment 3 is solution of assignment 3 is not given. It will be given shortly. And on the next class, I'll request for one extra class. On that, we'll solve the homework to 4, the assignment 4. It's already uploaded and it has, I guess, how many questions? Mm, yes. Yeah, it has around five questions. Okay. It's regarding the squid things, no? So yeah, we'll discuss this on next class. Thank you.